Welcome to our topic this week, which is going to be about the different ensemble models. We're going to start with decision trees, and then we'll look into the random forest, the Adaboost, and the gradient boost models. A decision tree learns a sequence of if-then questions, with each question involving one feature and one split point. The tree carves up the feature space into groups of observations that share similar target values, and each leaf represents one of these groups, right? So a decision tree is basically starting with a initial question. That question basically asks, okay, which feature should I choose? And within that feature, what split points should I choose? This, that question is based on a calculation which basically tries to minimize that value, right? Or maximize the gain of it. And we'll talk about that soon. So regardless of that, so it chooses one and then splits that into two different nodes, right? So, and it goes on like this. So at each question, at each node, the tree splits the data into smaller and smaller pieces. That's the main idea of how the decision trees work. And again, what drives this behavior, like how does it decide on what to do, we'll soon see that. So each leaf in the decision tree is responsible for making a specific prediction. In regression trees, the prediction is a value, right? It's a continuous numeric value. In classifier trees, the prediction is a target category, right? So it's a discrete value that's being predicted there. So the different terminology used, we have the initial node, which is called the root node. Then we have the splits. So these splits, they are called the branches. And then the nodes after the root node, basically the places where the questions are being asked, are called the internal nodes. And then it goes on like this until the very end, where basically there are no more splits done. So these are called the leaf nodes. You see a decision tree example here on the right, based on the famous iris data. This is obtained from the scikit-learn package in Python. So you can see here a few things. At the root node, the question that was found to be the best to be asked was the petal length. So the question says, okay, is this petal length less than 2.45 centimeters? If it is true, those data points will go to the left into this node. If that's false, they will go to the right into this node. So you see a value here, Gini, it says 0.66. That's the Gini calculation that's obtained from here. Another method used for splitting the trees is by calculating the entropy value, and that formula is shown here. They are very similar to each other. This P stands for the proportion. So the proportion of points in that node, okay? So initially the values are 50, 50, 50, as you can see. So that means there is equal number of points from each of the classes. There's 3 classes here, right? The versicolor virginica and the other type, which I said was a class. So there's 3 types of flowers, and there's 50 data points from each of them. So at the initial point, the Gini is quite high. So the goal of the decision tree is to decrease this Gini value. All right, by doing the split, it's trying to achieve that. So that's what drives this behavior of this decision tree, where it splits up into different branches like this. So after that initial question of whether the petal length is less than 2.45 centimeters, 50 of those flowers within this 150 have less than that value. So they were all on this left branch here, and 100 of them go to the right. So they have apparently petal length greater than 2.45. All right. And it also happens that 50 of this who went to the left are all from the setosa class. Hence this color was in orange, and it's quite dark orange. It's a pure node right now, as you can see. There's none of the other classes. So when that's the case, basically our Gini goes to 0. And that's the main ultimate goal of the decision tree, getting down the Gini to a value of 0. Because when it's 0, that means all the points are from the same class. That's a pure node. So it's basically the main goal of the entry, okay, reaching pure nodes. So when you look on the right node, there's 50-50 from each of the classes, right? So that means there is a lot of more work to be done here. It doesn't, one thing that really the entries hate a lot is that there are equal number of points from each class. That's the worst case scenario. So the first scenario here was the worst. This is also not good, right? So the Gini is 0.5 here. There's 100 samples. And then it makes a split. Again, another question based on petal length, but this time the threshold is 4.95. So if it is less than 4.95, sorry, I'm at this node. If the petal width is less than 1.75, everything will go to the left. Anything greater than 1.75 will go to the right. Okay, so when it went to the left, there is 49 from this middle class and 5 points from the right class. So this is pretty good. It's not still pure yet, but it's much better than before. So, and it says class versicolor, so that means most of the points in this node is from the versicolor class. All right. And in this node, it asks another question. Again, petal length is being used. The question is whether the petal length is less than 4.95. If that's true, it will go to the left. If that's false, it will go to the right. And so on and so forth. So it goes on until it basically reaches its, pure condition, right? So you can see here at the end nodes, the leaf nodes, this Gini is 0, the Gini is 0, 0, 0, 0, 0, 0, 0. This is also 0. Right, you can see that all the leaf nodes have a Gini of 0. So basically at this point, the tree realizes it cannot do any more splits because the Gini is 0, and there is no need to do any splits anymore. So then basically the algorithm terminates there. All right, so of course, just a quick note, we'll talk soon more about it, but once the tree grows more and there are more levels here, so that it becomes deeper, you might realize actually some splits, even though they are not pure, it's unnecessary, right? So the word overfitting should come to your mind here. So you see like this node, for example, here, right? There's only 6 points in it. It's already quite small, and there's 2 from the versicolor class, 4 from the Virginica class, right? So me personally, I would stop here, but again, because of the algorithm that this really tries to reach the pure condition, so it still continues to split here. But then you can imagine that the further the splits are made, the more the tree is oriented towards the data and the noises within the data, so it becomes more and more overfitting. So we will talk about, how can we stop this behavior soon. So, but just a thing that I want you to realize here. So this Gini, the calculation of Gini or the entropy, is basically used together with the information idea. So these show us the information. And the difference between these two levels, this is called the parent, and these two here on this level is called the children, right? The difference in their Gini values is called the information gain, okay? So since the decision tree tries to minimize the Gini value, the difference that also means that the difference between the parent node and the children node in terms of information is basically being maximized, right? So it tries to maximize the information gain. That's the another way to look at it. At the end, they are the same thing. So when training a decision tree, the overall goal is to decrease impurity. Impurity can be computed by using the Gini values or the entropy values for classification trees. And if you're dealing with regression, then basically it's the mean squared error within that node or the variance. It's the same thing. The difference in impurity between the parent node and the children's nodes is identified as the information gain. I just explained it. The split will only happen if the total weighted children impurity is less than the parent impurity. The best split is the feature and the threshold within that feature that will be used for the next split, right? and it's chosen based on the criteria of the largest information gain. So again, the difference between the parent node, the impurity value there, and the children impurity value, this is called information gain, right? Impurity can be calculated either by using the Gini index or the entropy values. So once those are calculated, difference between them, we try to maximize it. That's it, basically. That's the definition of the information gain. Okay. This nj and n is the total number of points from the parent, and the nj is the number of points in each of these splits being made, right? So this is n points here, and then this is n1, and this is n2, basically the number of points that end up in this node and in this node, right? And then the information or the impurity in this node, so that's I1, and impurity in this node, that's I2. That's the I here, and then we multiply this by this ratio, ni over n, n2 over n times I1, and n2 over n times I2. So we add them up. So that's the total weighted children impurity. So we want that difference to be as large as possible. And basically that's how the decision tree chooses the next feature and the split within that feature, okay, to maximize this information gain value. The decision trees are split by, so again, the important point here is that the feature is being chosen and then a split point within that feature chosen. So if it's a categorical value, one of the distinct values within that categorical value. If it is a numeric value, then basically it's a continuous spectrum, so at a value within that range of that numeric value is being chosen for the next split, right? So then the best split is chosen based on that. So for example, if the tree was trying to split this example here on the left, if this is the x, one of the variables that was being investigated upon, so let's say it tries these different thresholds and then actually finds that if it chooses this value here, then once that split is done, all the points from the blue class is on the left, all the points from the green class is on the right, so that's a perfect split. It reaches a pure situation, so it will choose this threshold within this feature here. So for two-class setting, that formula that I've seen before can be simplified a bit more, and I've shown here how you can do that within a coding environment. Let's say in this case it's Python. By calling the NumPy library in Python, you can easily calculate the Gini index, the entropy values, and the figure on the right shows how those look like for different proportions, right, between 0 and 1 for two-class scenario. And you see the blue line is entropy, the green line is Gini, and in terms of shape they are similar, right? Their height is different, but that's it. So that's why either using Gini or entropy will mostly give you the same solution for the decision trees. Misclassification rate is another thing that can be computed. However, that's not preferred in terms of decision tree optimization or decision tree classifiers. So what are the sum of the pros and cons of decision trees? The interpretability is important, so we can understand how the decision tree looks like, what it does. We can also explain to others, so it's quite useful in that regard. Minimal feature engineering is needed, so we're not too much worried about things like standardization and other things. Categorical features are actually better than numeric features, I would say, because of the less number of thresholds that are possible to be chosen within categorical features. It gives us what's it called, like a, so after you create the decision tree, you can look at the feature importance. That means feature importance is, in short, I would say, can be defined by how many times a feature is chosen, how high in the decision tree a feature is chosen, and those kind of things that basically show how important a feature is, right? Because if a feature is chosen at a higher level, that shows it's more important. And if it's chosen several times, again, the higher the better, then again, it shows how important that feature is in terms of splitting the data, right? If a feature is chosen only at the very end, or maybe it's not chosen at all, then basically, that feature basically does not show any value in terms of splitting the tree, right? In terms of the Gini or the impurity calculations, right? So basically that's why they are not deemed important. So that's why there's feature importance, which also basically can be obtained not only from the trees, but later on in random forest and other ensemble models as well. So basically it's an important thing that will help you, for example, in your feature selection, if you have many features to work with. So it's non-parametric, right? That's a good thing, so you don't need to worry about it. Of course, one of the things is that it's, because it's non-parametric, it's really everything is based on the data. So that also means a small change in the data will lead to quite distinct, quite, very different decision trees. A very small change will lead to that, so that's also means it's unstable. That's something that I would say actually can also be put under one of the negative sides of decision trees. It's fast in general, right? So that's also a good thing. So high overfitting, high variance is a problem because it tries to reach, a pure situation, pure condition. So it will split and split and split if it is not stopped by anyone else. So that will lead to a overfitting problem. The instability, as I said, it's very data sensitive, right? So small change in data, rather different decision tree, which is not good. And the accuracy probably is not generally as good as the other more complex, more advanced models out there. So it seems like overfitting is a major problem. What can we do to lower this overfitting problem, or maybe eliminate it, right? So what we can do is, for example, we can set the minimum number of samples required in at a splitting node, right? And the decision tree is, we want to split a decision tree. A node, right? So this is the node that we are in now. Well, actually, let me go to this example before. So I mentioned this kind of here. So we said, okay, if there's only 6 points in this node, do we still want to split it? In the upper node there was 54, for example. So we can set a limit here, a minimum number. We can say, hey, if it is less than 10 data points in the node, do not even attempt to do any split at all. So if we put such a limit, then basically there will be no split in this node done. So that means this won't even come to life, right? They won't be even born. So this is a good thing, because now we are, we are trying to stop the tree to grow further. That also means we try to stop any overfitting. So if this is the limit, for example, at 48 data points, it will try to do a split. At 54, it will do. At 46, it will do. Then there's 3 data points here, so it won't. So it, after this node, it won't do any split. So this won't happen and this won't happen, right? So this is a good thing to put some thresholds. And again, this threshold, of course, is based on your training set size. Here we had only 150 data points to start with, so maybe 10 is good. I don't know, if you had maybe 1,000 data points, maybe you can increase this to 50 to somewhere between 100. I don't know, if you had 100,000 data points, probably like 1,000 or maybe 5,000, somewhere around that could be a good number. Right, so again, it kind of depends on your data set size and how much, deeper you want to go with. But so it's good to set a limit there nonetheless. Setting the minimum number of samples required at a leaf node. So leaf node is the one at the end, right? So that's another thing. So after the split is made, let's say there was 100 data points here, and we make a split, and then 60 goes here and 40 goes here. This might be okay. But what if there was 100 to start with, and I don't know, only 5 goes here and 95 goes here? So this is okay maybe, but this doesn't look so good to me. So that's why if you put a limit there on your leaf nodes to have, let's go back to our main tree again. Let me see here, can I do some cleaning? How do I? Nope. Okay, I cannot erase this stuff. All right, so so these leaf nodes, let's take a look at them then. So for example, this split here. So we said with a inertial node where the limit is 10, it's okay to do a split, right? Because there's 48 data points here. And after the split, 47 of them go here and only one of them goes here. So this 47 is okay, but this one, I don't like it, right? So if I set a limit of leaf node having at least 5 data points, then basically it will do the split, but then it will look at the leaf nodes as well. So it will say, hey, after I do the split, there will be 47 in this left node, and there will be only 1 at this right node. So then basically this will prevent, this limit will prevent the tree to do the split. So this and this, both of them will not happen because it won't do the split. So this will be the leaf node. This will be the end terminal node. Here it will stop there, right? So as you can see, this again further prevents the tree from growing. So this, this is another method, an effective method to apply in terms of preventing overfitting. Setting the maximum depth of a decision tree. So you've just seen basically after, the main goal of doing these two is actually to prevent the tree from growing and growing further. So if you set a limit of maximum depth, so if you say, hey, I want my tree to go only, I don't know, 3 levels deep. So after 3 splits, it will just stop there, right? This is basically another way of preventing the tree from growing too much. Again, here different values can be chosen, can be tried upon. So at the end, all these are hyperparameters. So different values can be examined with, experimented with, and then the best combination can be chosen that leads to the best validation accuracy or validation performance for a decision tree. The pruning is another way. So what pruning says is this: so let the tree grow, don't touch it, don't interfere with it, let it grow as much as it wants to. And then once it's fully grown, then we start intervening. So we start cutting from the end. So it's like pruning a tree, a real tree outside, if you've ever done it or if you've seen people do it. So they do it because it helps the tree to become more healthy, to grow better. Because if you don't do that, especially for fruit trees, they will just become like a bush. It won't be good for the tree. So we don't want the tree to grow like uncontrolled, in an uncontrolled way. We want to control it. So here the same idea. So we let it grow, and you can think of that like the tree growing in the season, and at the end of the season we prune it. Okay, so the pruning starts at the end. It cuts off branches. The main idea here is that if you get rid of this node, how much of a difference will it make in terms of the performance of the tree, or the error? The error will increase, but how much will it increase? There's a limit there, so the tree will be okay, or the pruning algorithm will be okay, that the error increases until some point, and after that point it basically says, okay, we got to stop here, because if you go any further, then the tree will be cut too much. So we don't want to do that too much. So this is called pruning in short. Again, this is also another effective method. Now my just personal idea is that if you apply these methods that kind of interfere with the tree, you won't need this pruning done at the end. So, but you can also explore pruning and then see how it does. Okay, so here's an example of the effect of the decision tree depth into its overfitting. So you see at 15 depth, and then it decreases, right? You can see how overfit it is. Let me explain this figure. So the blue line is the actual real line we start with, and then these gray points are created out of this blue line. So random points are created with random error added to that blue line. So then basically this decision tree is a regression tree that tries to fit this this gray points. Okay. So as you can see, if the tree is too deep, then it really goes overfitting. You can see all these zigzags happening quite a lot. But if it is decreased, this number, so we limit the growth of the tree, then it becomes smoother, right? And after some point, of course, it becomes too smooth, so then it's underfitting. So somewhere in that value is a good value that kind of fits the data best. Okay, and I would say maybe 4 level deep or so is good, or maybe 3. But you know, this data is not probably a very good example to fit a decision tree anyway. So that's another question to be asked there. But you get the idea. Okay, so let's go to the next one. So we have a minimum node size example here. Same idea, the data is created in a similar way. So we fit a regression tree here. If we have a minimum number of observations as a threshold there, right? So when the value is too small, it's overfitting, right? So at the initial point, it's 1. So we are even okay for the decision trees to split the node, the node, even when there's 2 data points at the initial point. So that's why it does a lot of splits. So that means overfitting. And that's why it was, there was a lot of zigzag at the beginning there. But then if you increase this number, so then it does less and less splits. So the tree is smaller, then, basically it doesn't overfit as much as before, as you can see. All right. Okay, so I would say actually, trying to improve decision trees is one way, or we can just take many trees and work with them together. So then the idea of ensembles comes in. All right. So decision tree, the learning algorithms, are based on heuristic algorithms such as the greed algorithm, where basically they do locally optimal decisions, right? At each node, the best decision is being given. Now, in such algorithms, it's no guarantee that we will get the globally optimum solution. So this can be mitigated by training multiple trees in an ensemble learner, where the features and samples are randomly sampled with replacement. Okay, so here's some different random subsampling techniques that's being applied on decision trees in terms of coming up with different ensemble models. Right, so they basically focus on either sampling from the data or sampling from the feature or sampling from both. And these are given at the end, so you can take a look at them if you like to. So what is random forest then? So it's an ensemble method designed for decision tree learners, right? So it's basically made up of decision trees. Random forests are an improvement over the bagging models. So, right, the bagging models was saying, hey, randomly subsample your dataset and build models based on that. So the random sampling of data objects and features is applied in random forest. So there's 2-step randomization here. One is on the data points and one is on the features. So we will create bootstraps for each tree. This is done once at the beginning of each tree, right? So each tree is grown on a different data set basically. And then randomly select a subset of features. So this is done at every splitting node, right? At every splitting node within that tree. So let's say we have features from 1 to 10. A subsample will be selected. Maybe randomly 3 points are selected, and let's say they are F2, F5, and F7. So among these 3 features, the best split will be done at this splitting node. Okay, so it won't look at every feature all of these 10 features in this node, it will only look at this three features to select from. So that's the randomly selecting of subset of features. Okay, so two-step randomization is done in a random forest. Another thing is trees are fully grown, so that's another interesting point in random forest. So there's high variance in the trees, but the idea is that we combine them. Okay, at the end we will have many trees, so when we take the average of that, we will reduce that overfitting caused by each of the trees, so then it will become more generalizable. Right, so by averaging we decrease the variance in the trees we have. So how does the random forest algorithm look like? We draw a random bootstrap sample of size n. So we randomly choose n examples from the training dataset with replacement. We grow a decision tree from the bootstrap sample, and at each node we randomly select the features without replacement, right? We split the node using the feature that provides the best split according to the objective function, and in this case objective function is minimizing, the impurity or maximizing information gain, same thing. And then we will repeat these steps, right? So that means we will grow k number of trees, so many trees basically. And then at the end we aggregate the prediction by each tree to assign a class label by majority vote. The feature subsize selection, so you might wonder, okay, how many features am I going to select randomly? So there is no actual rule for that, so that's another hyperparameter that we can investigate in decision trees, in random forest or ensemble models. But generally it's like for classification trees, we take the floor of the square root of the number of features, and for regression it's the number of features divided by 3. This is no rule or anything, or it doesn't mean these are the best values. It just maybe it will give you a good guidance on the initial as an initial value to start with. And if I'm not mistaken, it's like learn by default. If you don't do anything with this, I think it's like set the square root of the number of features, the default value. Okay, so let's look at how a random forest is built. So here, each of the gray lines, you see the straight lines, is basically a decision tree, okay? And then the average of those decision trees is shown in that blue line there. Again, this is a regression kind of a problem you're trying to solve, okay? The dots that you see that constitute the data set, again, each decision tree is grown on a different data set, right? It's randomly subsampled, okay? So that's why each decision tree is different, okay? And here the important point is that at the very initial, when there was only a few trees, right, the random forest was not very good, right? So it was, as you can see at the initial point here, it's basically the same as a decision tree, and it's not generalizing very well, right? But then over time, as there are more trees, the average basically shows a better pattern that kind of fits the data better than each of the individual trees there, right? So by taking the average, we are getting rid of the overfitting and kind of, move towards the mean of the points, as you can see. So we are fitting the data much better. So that's the power of random forest here. The OOB is the out of bag in random forest, so that stems from the creation of the decision tree datasets, right? Because bootstrap data was created, so it means the same number of points are selected randomly with replacement, right? Some points can be selected more than once, and some points will never be selected. And on average, 1/3 of the points are not selected. So those points that are not selected in each of the decision tree dataset can be used as an out-of-bag data or like a validation data to test your random forest on. So in this example, which was taken from scikit-learn website, what they do is they grow the trees, right, from left to right. The number of trees that are grown increases, and then at each stage, basically this error shows the error that was, after growing each tree, they were tested on the points that were not selected, so the out-of-bag error rate, right? And then, it initially, the error rate here shown is the average of 20 trees, okay? And then over time, of course, we will have more trees, so the average is done over those number of trees here from left to right. And each color shows the maximum number of features chosen. So we were talking about that before. So the maximum number of features is chosen is in blue is the square root number of features. The orange one is taking log 2 of the number of features we have, and green basically chooses everything. So this none means, okay, include everything. Do not do any sub-selection of the number of features. Just when, look at every available feature we have. So as you can see at the begin, the worst performer is the one with log 2. The best one is the one that looks at every feature, the green one. But then the green one doesn't change performance. So I think this is quite interesting because it keeps looking at every feature from the initial point until the end. So the number of trees doesn't have much effect when you do that. But when you sub-select the features, then it seems like log 2 and square root are performing better, and in this case square root did a bit better than the log 2 when you had more trees. So this stems from the fact that the trees grown in blue and orange are more diverse from each other because it's the randomly selection of the features have an impact. And at the very end, when you take the average of those, and when you have more trees, then basically they perform better. Okay, so it's kind of the power of having different voices, different ideas, and then the average, combining them, taking them all together gives you a better performance. So this here, the trees are not that different than the green one. They are quite similar to each other. And which brings me to the point of tree variety. So if we were to use the same data set with the same features, right? If there was no sub-selection of data and also no sub-selection of features, then each of the tree grown will be identical. They will be 100% similar. I mean, not similar, they will be 100% exactly the same thing. So then basically there's no point in random forest if you were to do that, right? Because one tree would be enough for this. So some ideas that, basically we are applying in random forest is backing, so randomly subsampling the data, and also random vectors input. That means at each node we randomly select some of the attributes, right? Here the main goal is we want to decorrelate trees and increase variety between the learners. But can we increase it even more, this variety, this diversity? Can we do that? So decreasing the size of the bootstrap sample. Okay, so we said, okay, we have n data points. We will create bootstraps out of n data points with replacement. But we can also actually decrease the number of the points we are selecting. So instead of n, maybe we can go with n over 2 or basically some number less than n. If you decrease the size of the bootstrap, then we will have more diverse trees. Okay, this will increase the diversity among the individual trees. The probability that a particular training sample is included in the bootstrap sample is lower. If you decrease the number of data points, then the data sets will be more diverse because they are smaller, right? And then since each bootstrap created will have more chance of selecting data points that are different from each other, right? This basically these two ideas, right? Because we are doing with replacement, right? Instead of, let's say we had 100 data points, instead of creating a bootstrap with 100 data points, if we were to create a bootstrap with only 50, then there's less chance of the same data points appearing in this 50 data points. And so each tree will be grown on quite different data sets, right? So this will increase the diversity in the trees being created. So shrinking the size of the bootstrap sample may increase the randomness of the random forest, and it can help reduce the effect of overfitting. And we can apply the same logic to features as well. So, right, some chosen values is like square root or log 2, but we can even lower this amount even further. such that at each node there will be even less features to consider, then this might increase the diversity as well. Now, of course, if you decrease it too much, then that might not be a very good idea. But again, if you decrease it to some reasonable value, then the trees created will be less similar to each other, right? Because here the main idea is that if there's some good feature, right, every time it's being selected in the tree in the node, it will be used for the splitting, because it will have a dominance over the tree. And if that feature was chosen over many trees, then it will those trees will show similar behavior. But if you decrease the number of features to be considered, then the chance of that dominant feature to be selected as one of those features decreases. And since that chance decreases, then the features selected at each node will be quite different from among the trees. So each tree will create different kind of trees from each other. Okay. So in turn, this might increase the diversity in your decision trees and in your random forest at the end, or your ensemble model at the end. So these ideas, although we talk about them in random forest now, it's not something that can only be applied in random forest. These can also be applied in different kind of ensemble learners, even though it might not fit into their classical definition directly, right? So these also don't fit into the classical definition of random forest. But again, we can try these ideas and see if we can make the random forest even better. All right, so some of the advantages of random forest is that generally it is a good accuracy. It's generally definitely better. Well, I would say most of the times better than a decision tree. And that's the main goal, right? The reason to create many trees is to have a better model at the end. Parallelization can be applied. That means because each tree is grown on a different data set, and they have no connection to each other. So that means they can be grown simultaneously. That means parallelization can be applied. Categorical variables are, of course, welcome in random forest because decision trees are good with them anyway. So random forest is also good with them. So what's the main goal of random forest? It's to decrease the variance, the high variance in the decision tree, right? When that happens, the bias will increase, right? There's always a balance between the bias and variance. So when this goes up, this will go down. When this goes down, this will go up. So the tree is trying to decrease the variance. So this will go up. But again, how much will it go up? If it goes up only a little bit compared to a large decrease in the variance, that's a good thing. And that's what the random forest achieves. So that's why random forest is a good algorithm. And yeah, that's the main benefit of random forest there. So let's look at the other ensemble types now, the boosting method. Here, the boosting, what they do is they will combine weak learners, and the weak learners are grown sequentially, right, on the whole dataset to create a strong learner by capitalizing on the misclassification error of the previous models. So we iteratively learn weak predictors to improve upon the errors of the previous predictors. The final decision is the weighted sum of the results of the weak predictors. Some examples are Adaboost, gradient boosting, XGBoost, and so on. So what is this weak learner? Well, weak learner is generally like a very simple model that at least achieves like about 50% accuracy. Okay, so it's slightly better than a random chance a coin flip. So a decision tree with a single level, single split, this is a weak learner. This is also referred as a decision stump. Okay, and it's generally the main building block of Adaboost learners. So just a single split each time, just basically what this means is that a decision tree will be, will choose one of the features and the best split among that feature, and create a decision tree from that, and that's it. And then the next tree will continue like this. Okay. So the pseudocode for Adaboost is we train the first weak learner on the first dataset, and then we will repeat the following. Okay, so after a weak learner is trained, the points are modified. What does it mean? The points that are incorrectly classified are enlarged. That means the incorrectly classified points have more importance in the next decision tree, right? So because they were incorrectly classified, that means they're hard to classify. So we put more emphasis on those points in the next decision tree. The ones that are already correct, that means they are good. There's no problem with them. They are easy to classify. So basically their importance will decrease. So we are not that much concerned with them anymore. You can think of this, the idea is like, okay, you study a chapter or you prepare for an exam, right? And then you kind of made some exercises yourself. And then based on those exercises, you realize you're good in this portion of the book, chapters, I don't know, 3 and 4. You're not that good on 5 and 6. You're very good on 1 and 2. So the next day when you start studying, you won't even look at this because you're good to go. You will put much more emphasis on this. So let me put this actually, and maybe a little bit emphasis on this as well. Okay, because you're not that good on 5 and 6, so you won't study more on this. You're very good on 1 and 2, so there's no point on spending any more time. It's just a waste of time now because you want to get good at these chapters. Okay, and among these 3, 4, 5, 6, you put more emphasis on 5 and 6 because you did not do good on the exercises yourself. This idea here in Adaboost, when it sees it making errors on some point, it will put more emphasis on those. So in short, this is how we can look at this problem. So after iteration 1, let's say these are the points that are misclassified, right? So these are the points. So basically you can see that their importance has increased, and these were correctly classified, so their importance has decreased. They became smaller, right? So these points, they were also correctly classified, so that's why they became smaller as well. But in this classification, they were misclassified. These points, these minuses, you see that they're from the negative class. In the next iteration, they will have more importance, right? So in this iteration, these misclassified points from this iteration 1 are correctly classified, so their importance decreases. So you see it's a dynamic behavior over time. It doesn't mean that one point will always, keep increasing in importance based on whether it was accurately classified or not. Its importance will either decrease or increase. So at the end, also another thing here that's important is we calculate a value, an amount of vote, let's say, for each of the 3. That's basically its weight. So, and that weight is determined by how good that decision tree was in terms of its accuracy. Highly accurate trees will have higher vote, and low accurate trees will have less vote. So these are the vote amount for each, or the weights of each tree, right? And at the end, their vote amount times their prediction for a point is being multiplied, and then we add them together to come up with a final solution. So that's how the Adaboost works, right? One after another. It's a sequential process. It goes like this. So that's why, for example, parallelization is not really possible here, because each tree is dependent on the previous tree. Okay, so that's why it will go in a sequential forward, building manner like that. So this alpha value, see here, this alpha value, which is these weights. Okay, so it's based on how good the model is. This J is the error in that tree there. So let's see an example of this, like what does it look like, a bit more detail. So this is the calculation. So the weight grows exponentially as the error approaches 0. Okay, so as the error, so that means the accuracy goes 100%, then the weight will grow exponentially, right? At error rate 0, the weight is the largest, and the error rate 1, it's the lowest, as you can see. So better classifiers with accuracy above 0.5 are given exponentially more weight. So 0.5 is a critical point here. It's like the middle node. And at 0.5, the weight is 0. Okay, at error 0.5, the alpha value, the weight of the decision tree is going to be 0. Because a classifier with 50% accuracy is no better than random guessing, so we ignore it, right? Weight grows exponentially negative as the error approaches 1. Classifiers which are worse than 50% accuracy will get a negative amount. So here the ideas of this point is this. So now I don't think this will happen, but if it were to happen, a tree that has larger than 50% error, right? That's even worse than a coin flip. That's this portion here. That means that we should just take the opposite of what this entry is saying. That's what it is. Because if something is at 60% error rate, and assuming just two classes here, then basically if you just take the opposite of this, then this will this will go down to 40% error. Right. So that's why I don't, in practice, I don't think this will happen, that it goes to less than 50% accuracy or more than 50% error. But this basically is a, this blue line is just to show this calculation, how it behaves throughout the whole spectrum from 0 to 100% error rate. Okay. And another thing in practice, if this were to happen, the alpha value is set to 0, not like a negative value, but it's set to 0. So let's look at like some numeric examples here. If you have an error of 0.2, based on this calculation, we would get a weight of 0.693. At 0.5, if you put it into that calculation, you get 0. At 0.8, so that's basically the, right? As you can see, it's the mirror of 0.2, it's the opposite. So at 0.8, the error is minus 0.6, and at 0.9, we get an error, a vote of minus 1.09. So that's here some area. So, right. So for error rate of 0 or 1, there is a very small value is added to both the numerator and denominator to prevent zero division or undefined error from happening, right? So ln 0 is undefined and ln 1 over 0 is undefined, and also probably will get a division by 0 error here based on this formula, right? So some small values added here in both. And again, the thing is that if there's a case where the decision tree had larger than 0.5 error, the alpha value is set to 0 rather than a negative weight. Okay, so this was just to clarify this alpha value. Gradient boosting is another boosting method. It's it's a bit more advanced. It was built after or invented after Adaboost, so it's a bit more advanced. This is how the algorithm looks like. The main thing is that the gradient boosting directly works on the errors themselves. Okay, so it doesn't work. It works rather different than the Adaboost actually. So it tries to fit a tree based on the errors. Basically, when I say based on errors, I mean directly on the errors themselves. Okay. So it's rather different. The idea is that once we do that, and at the end when we combine these trees together, then we will get a better solution. All right. And again, we will do examples on these during class time. So the algorithm looks a bit, I would say, difficult. It's hard to understand maybe. But again, actually, once we go over the example, then you will see that it's quite easy to understand how it works. So how does the gradient boosting work? So here we, instead of trying to emphasize the problematic instances by assigning weights and resampling the dataset, the gradient boosting builds each base learner on the previous learner's errors. Okay, it's more generalized framework than Adaboost. It uses decision trees of varying depth, so generally medium depth is being used. So it's not stumps, it's not a single deep tree, but maybe like a medium size. So it's smaller than nanoforms and definitely larger than the Adaboost. It fits an additive model, an ensemble model, in a forward stage-wise manner. In each stage, introduce a weak learner to compensate the shortcomings of existing weak learners. So the idea is, okay, we made errors in the previous tree, let's decrease that error in the next tree. Okay, that's how it goes. So improvement over basic gradient boosting could be basically the ideas that we thought of previously can be applied here as well. Okay, so one thing is we can, here each tree has an equal weight, so we can, for example, change that, and we can make it a weighted tree. So just like Adaboost, we can say, okay, maybe each tree should have a different amount of say based on how accurate it was able to predict. That's one idea. We can also introduce random sampling. So this random sampling idea of both subsampling the rows, right, the data points, or subsampling the columns or the features, the variables, that's not being applied in gradient boosting. So the stochastic gradient boosting is saying, hey, maybe we should take those ideas from random forest and apply it here as well. That's another way to maybe improve on gradient boosting. And then the three constraints that we have seen before can also be applied in gradient boosting. Okay, things like the number of trees, tree depth, the number of points in the leaves, number of point observations per split, and things like that could be applied in gradient boosting as well. Okay, finally, let's just make a quick comparison between these bagging and boosting methods. And generally, when we say bagging, we refer to random forest here. So bagging is good for reducing the variance, the high variance problem, right? Whereas the boosting reduces the bias. That's its main goal, right? After each tree, it tries to increase the complexity. So actually the variance goes up and the bias goes down in boosting. So that's they are quite different in that regard from each other. Bagging and boosting are quite different. Bagging helps to prevent overfitting, right? And boosting is good when with weak models and there's underfitting. Bagging, the models are built from random subsets of features. In boosting, the models are built on all the available features. Okay, that's another difference there. Bagging, the training data is chosen based on the bootstrap process and all instances are equally weighted. Right? So we have the bootstrap process and all instances are equally weighted. In Adaboost, the instances have an unequal probability of appearing in subsequent models, and ones with the highest error are weighted higher and appear most. Right? And in bagging in random forest, all models are equally weighted during training and inference. In Adaboost, we have something called the weights, right? The alpha value we just talked about. So it allocates higher weights to a learner with good classification result on the training data. So bagging can be parallelized since trees are mutually independent, right? But in gradient boosting or Adaboost, each tree builds each base learner on the previous learner's errors, right? So we cannot really apply parallelization here. Okay, so these are some of the main differences between bagging and boosting. And when we say bagging, we here mainly focus on random forest. So that's it. The final things to say, I would say ensemble models are in general good models. You will generally get good results even without doing much hyperparameter tuning. Both bagging and boosting have their, they are good models, I would say. So they both can be explored and applied. Random forest, Adaboost, gradient boosting. They're mostly, based on distant trees. So distant trees are good building blocks for these more advanced models here. So, and finally I said I was going to show you these references here. So those are here. So thank you for listening and good luck applying ensemble models. Thank you. Have a good day.